Welcome to Echo 341, Studies Section 1, Linear Models and Matrix Algebra. Introduction. From your knowledge of market equilibrium analysis, you will notice that for a two-commodity market, it is relatively easy to establish and solve for equilibrium of variables of interest. However, in the real world, markets are interwoven. For instance, the demands for beans may not only depend on its own price and price of palm oil, but also on the prices of rice, pepper, and even yam. In particular, it is possible to have an commodity market, in which case it will certainly be difficult to solve for the variables of interest simultaneously. In this study section, we shall present a method that is capable of handling this problem and the related ones. This method is called matrix algebra. Matrix algebra provides a compact way of writing an equation system, even an extremely large one. Also, matrix algebra allows us to test for the existence of a solution by evaluation of a determinant. Furthermore, it gives a method of finding that solution if it exists. Matrix algebra becomes more useful when we encounter comparative and dynamic analysis and also in handling complex or simple optimization problems. Objectives. At the end of this study section, you should be able to 1. Arrange equation systems in matrix format. 2. Find the determinant of a simultaneous equation. 3. Compute the inverse of matrix. And 4. Apply Cramer's rule in solving simultaneous equation system. Content. A matrix is a rectangular array of numbers, parameters, or variables. The members of the array referred to as the elements of the matrix are usually enclosed in brackets or sometimes in parentheses or with double vertical lines. Consider a general system of m linear equations in n variables, bracket opened, x1, x2, x3, xn, bracket closed. Such linear equation can be written as follows: a11x1 plus a12x2 plus a13x3 plus plus a1n(xn) is equal to v1. a21x1 plus a22x2 plus a23x3 plus plus a2n(xn) equal to v2. a31x1 plus a32x2 plus a33x3 plus plus a3n(xn) equal to v3. Equation 1.1. am1x1 plus am2x2 plus am3x3 plus plus amn(xn) is equal to vm. In equation 1.1, the variable x1 appears only within the leftmost column, or in general, the variable xg. j equal to 1, 2, 3, m appears only in the jth column on the left side of the equal sign. The double-scripted parameter symbol aij represents the coefficient appearing in the ith equation and attached to the jth variable. As an example, a32 is the coefficient in the third equation attached to the variable x2. The parameter vi represents the constant term in the ith equation. Therefore, equation 1.1 contains 3 ingredients in equation system. These are a set of coefficients aij, a set of variables x1, x2, x3, to xn, a set of constant terms v1, v2, v3, vm. It is possible to arrange these as arrays and label them respectively as matrices A, X, and D, as in A equal to bracket open A11, A12, A13, A1n, A21, A22, A23, A2n, A31, A32, A33, A3n, AM1, AM2, AM3, AMN, bracket closed. X is equal to bracket open X1, X2, X3, Xn. That is in column. V equal to bracket open V1, V2, V3, Vn, also in column. Equation 1.2. Let us give an example to illustrate further, assuming we have a linear equation system as follows. 3x1 plus x2 plus 5x3 is equal to 6. 5x1 minus 3x2 plus x3 is equal to 15. 7x1 minus x2 plus 3x3 is equal to 11. We can use the idea of equation 1.2 to write the above equation in matrix form as follows. A equal to, parenthesis open, 3, 1, 5, 5 minus 3, 1, 7 minus 1, 3, parenthesis closed. X is equal to, parenthesis open, x1, x2, x3, parenthesis closed. V is equal to, parenthesis open, 6, 15, 11, parenthesis closed, equal to equation 1.3. What you should note is that the coefficient matrix both in equations 1.2 and 1.3 are separated not by commas, but by blank spaces only. This is how we represent linear equation system in matrix form. Commutative, associative, and distributive laws of matrix. In ordinary scalar algebra, the additive and multiplicative laws obey the commutative, associative, and distributive laws as follows. Given matrix A, B, and C, commutative law of addition, A plus B is equal to B plus A. Commutative law of multiplication, AB is equal to BA. Associative law of addition, bracket open, A plus B, bracket closed, plus C is equal to A plus bracket open, B plus C, bracket closed, is equal to B plus bracket open, A plus C, bracket closed. Associative law of multiplication, bracket open, AB, bracket closed, C, is equal to A into bracket BC, bracket closed. Distributive law, A into bracket B plus C is equal to AB plus AC. However, in matrix operations, most but not all of these laws are applicable. The commutative law and distributive laws of addition hold in all cases. For instance, given matrices A, B, and C, the commutative law of addition says that A plus B is equal to B plus A. For associative law, bracket open, A plus B, bracket closed, plus C is equal to A plus bracket open, B plus C, bracket closed. Thus, bracket open, A plus B, bracket closed, plus C is equal to bracket open, B plus C, bracket closed, plus A. Matrix multiplication. Matrix multiplication is not in all cases commutative. For instance, given matrices A, B, and C, AB is not equal to BA. This holds in all cases except when A is a squared matrix and B is an identity matrix, that is, AB is equal to BA. If A is a squared matrix and B is equal to I, where I is identity matrix. Another case is when matrix A is the inverse of matrix B, that is, AB is equal to BA, when A is equal to B raised to power minus 1. Another case where commutative law applies is in the case of scalar multiplication, that is, given scalar V and matrix A, then AV is equal to VA. Associative law of multiplication. For matrices A, B, C to be conformable for multiplication, it must be the case that each adjacent pair of matrices is satisfied. That is, if A is of M by N dimension and C is V by K dimension, then conformability requires that B is N by V. A, M by N, B, N by V, C, V by K. If the conformability condition is met, the associative law states that any adjacent pair of matrices may be multiplied out first, provided that the product is duly inserted in the exact place of the original pair. Distributive law of matrix multiplication. Matrix multiplication is also distributive. In the case of distributive law, the conformability conditions for addition as well as for multiplication must be observed, that is, given matrices A, B, and C. A into bracket B plus C is equal to AB plus AC, pre-multiplication by A. B plus C in bracket is equal to BA plus CA, post-multiplication by A. Identity matrices and null matrices. Identity matrix is defined as a square matrix with ones in its principal diagonal and zeros everywhere. Principal diagonal is the line running from northwest extreme up left to southeast extreme down right. We denote identity matrix by I. If we want to indicate identity matrix, we may write I2, I3, meaning that the identity is of 2 dimensions and 3 dimensions respectively. In general, IN into bracket n is equal to 1, 2, 3, ... k bracket closed means identity of dimension n. One important role played by identity matrix is that it represents number 1 in scalar algebra. As we know, for any number A, we have 1A or 1A is equal to A. Also, for any matrix A, we have this relation. IA is equal to AI is equal to A. Equation 1.5. Identity matrix has a special feature in matrix multiplication. For instance, it is possible to insert or delete an identity without affecting the matrix product, since AI is equal to IA is equal to A. Now consider the associative law of the form A M by N, I N by N, B N by K is equal to A I in bracket B is equal to AB is equal to N by N, N by K, which shows that The presence or absence of I does not affect product operation. An identity matrix remains unchanged when it is multiplied by itself any number of times. Any identity matrix with such property is called an idempotent matrix. Idempotent matrix is equal to AA equal to A. This is the end of study section 1. Thanks for listening.